Today I want to talk to you in more detail about this example on the geometric distribution. We previously considered the experiment of tossing a fair die until it lands on number 4, and we had previously calculated the probability it takes 3 tosses of the die to land on 4. We discovered that this led to a geometric distribution. The geometric distribution is summarized by this density, geometric density that is in this box, and that probability density formula, which is very nifty for calculating probabilities. I want to go through an example calculating a probability that's a little bit more involved, and I want to remind us of some things that we know from calculus. So an infinite geometric sum, and the infinite being this sum from j equals 1 to infinity of a times r to the j, has the sum a divided by 1 minus r. Okay? The finite sum is a little bit different. The finite sum has this more complicated formula, and it's highlighted in part by blue. I'm not going to rewrite that, but it's a little bit more complicated. So the first question that we're going to ask is, what is the probability it takes more than 3 tosses of the coin to land on heads? So we're asking the probability x is bigger than 3. Another way of writing that would be x is bigger than or equal to 4. And now, because we know this is a geometric distribution, we can use this geometric density right here. Okay. So x being bigger than 4, that will start with p of x equals 4 plus p of x equals 5, and it continues infinitely because it could take a lot of tosses to the coin of the die to land on 6, potentially never landing on 6, or requiring a really large number, and that really large number keeps going. So we have this infinite sum. So I kind of gave it away. We're going to use that infinite sum formula. But first, let's calculate each of these probabilities. Each of these probabilities is given by this geometric density, and p is equal to 1/6 here. Okay, so x is 4 will be 5/6 1 minus p, and we'll have 3 failures and 1 success. Then p of x being 5, that'll be 4 failures and 1 success, and so on. Okay. I could have written this as the sum from j equals 3 to infinity of 5/6 to the j times by 1/6. Okay, if I wanted to really write down the infinite sum. And yes, it would matter that this j right here starts at a different value than the j listed here. Okay. But I'm going to highlight perhaps this form of the infinite geometric series, and I'm going to make use of that. Okay, because I have something similar here. I see every term in this probability has a factor of 1/6, so I'm going to take that out. I see also that every term has a factor of 5/6 cubed, so I'll take that out. And when I rewrite this, I'll have 1 plus 5/6 plus 5/6 squared. My next term would be 5/6 cubed, and that's comes in the ellipses from the previous line, and it keeps going infinitely. So I can use this formula with a being that term and r being 5, 6. So if I want to calculate this probability, it'll be 1/6, which is a, times by 5, 6 cubed, times by, well, so that will be a, times by 1 divided by 1 minus r. So 1 divided by 1 minus r, and r is 5, 6. Okay. Now we do see that this denominator 1 minus 5, 6, hey, that's going to be 1 over 1/6, so that will cancel with that. That'll be 5, 6 cubed. And that's the probability it takes more than 3 tosses of the coin to land on a heads. So that was a pretty nifty example. And this, in case you're wondering, is 0.578. So 57.8% chance it takes more than 3 tosses of the coin, or put another way, 4 or more. You might be wondering, could I calculate this probability in another way? And the answer is yes, you can. So the probability x is bigger than 3. We could have used the complement rule. And we need to make this statement false, the statement that x is bigger than 3. Well, for that statement to be false, x could be 3 itself, it could be 2, or it could be 1. So that's another way of writing it. And this will be 1 minus probability x equals 1, minus the probability x equals 2, minus the probability x equals 3. And then you have to calculate each of these probabilities with the geometric distribution, and you will also get 0.578. In some situations, this would be easier and quicker to use the complement rule. Feel free to use the complement rule in that situation, but a common mistake that I see is that people will just subtract off one of these probabilities, namely the one that x equals 3, and they'll forget about the other two terms. Let me ask you another question here. What is the probability it takes between 3 and 10 tosses of the coin? And we're going to include the possibility of 3 and 10. So we'll keep that in mind because that's an important and ambiguous distinction. So I'll say including endpoints. Okay. So the probability that you're being asked to compute is the probability x is bigger than 3, bigger than or equal to, or less than or equal to 10. And that's just this summation from j equals 3 to 10 of this 5, 6 to the j times by 1/6. Well, you guessed it, this is a finite sum, so we need to use the finite geometric sum formula. I'm going to write it as a times 1 plus r cubed, etc. Okay. And if I did this, this will be the probability x equals 3 itself plus probability x equals 4, etc. until probability x equals 10. So this will be 5/6 squared times by 1/6 plus 5/6 cubed times by 1/6, then a whole lot of probabilities in between until we get to 10, which will be 5/6 to the 9th times by 1/6, and I can write it in that a times 1 plus r. Okay, and I'm going to do that by pulling out a 1/6 as I did before, pulling out a 5/6 squared, and I'll get 1 plus 5/6 until, well, the last term will be, I already have the 1/6 accounted for, and I already have 2 5/6 accounted for, so this will be 5/6 to the 7th. Now, this will be A, this will be R. I'm going to use this little formula, and I'm going to pull A out. So that is, I'm going to write this as A times 1 minus R to the m plus 1 divided by 1 minus R. Okay, great. So let's rewrite this. We'll get 1/6, which is A, 5/6 squared, times by 1 minus R, that's 1 minus 5/6. We need to look at that formula one more time. 1 minus R to the m plus 1. Now, you might ask yourself, what's m? So we'll just need to make sure we know what that is. This will be 5/6, and we just need to figure out what power goes there. If we look at this formula, m is the highest power of R when it's pulled out. That will be this value right here, the 7. So I'm going to write this as 7 plus 1. And this is the probability that you have to compute. We've basically computed it. If you want it in decimal form, you'll have to put it in your calculator. So this was just an example to see how you can start with a problem that you need to realize use the geometric distribution. Once you have that formula, you can use this density to calculate probabilities, but oftentimes you may need to use the geometric series from calculus, the finite or the infinite form, or if it's tangible, you can use the complement rule. That is, if subtracting the complement leads to less terms that you can do in a realistic amount of time, you would want to do that. Okay. Thank you very much.